have Mahesh Chandran from the Indian Institute of Technology in Bombay, who is going to tell us about asymptotic quantum correlators.
Okay. Am I audible? Yeah, okay. Okay, so first I'd like to thank the organizers for giving me an opportunity to present my work here in this conference. So without much ado, I'll begin. So the universe as we know it is mostly homogeneous, but as we see from the CMB, the cosmic microwave background, which is a snapshot of the density distribution in the early universe, you see that there are slight inhomogeneities present, which basically arise from vacuum quantum fluctuations. And these fluctuations, after being stretched out to cosmological scales during a very early period during the expansion of the universe, they freeze out, and basically they are treated as classical stochastic entities instead of quantum fluctuations themselves. And this is what is identified as the quantum to classical transition problem. So in order to give a little bit more context, what actually happens is that these fluctuations can be treated at different wavelengths, and they get stretched out during the expansion. They cross the Hubble radius at some point and re-enter the Hubble radius at a later point during the expansion of the universe. And somewhere along this line, there was a quantum to classical transition. And after they re-enter, they're treated as classical stochastic entities, basically. But what I wanted to look at is how quantum entanglement can help understand this transition and whether it can capture any of these signatures in any meaningful way. Okay, so the toy model that we look at is a time-dependent massive scalar field in 1+1 dimensions. As you can see, there's a time-dependent mass term over here. And we have to deal with some sort of regularization procedure in order to get quantities that do not diverge in the end. And so what we perform is a lattice regularization. Basically, we place the degrees of freedom of the scalar field on a lattice. And what is profound about this is that if we treat fluctuations propagating in time-dependent backgrounds for any scenario, 1+1, 2+1, or 3+1, and if you exploit spherical symmetry, for instance, in the latter case, you can in principle write down the Hamiltonian for such systems as a chain of coupled harmonic oscillators with a time-dependent coupling and frequency. And in order to go about solving the system, what you do is you perform a decoupling of the Hamiltonian, you diagonalize it, and you obtain the normal mode spectrum of the system. And in the 1+1 dimensional case, in flat spacetime, you get equation 4. And now when you solve the time-dependent Schrodinger equation for each of these normal mode, you basically get a form-invariant Gaussian state, provided that you start with the Gaussian state. It will retain its Gaussian structure. And exactly at t equal to 0, when you start the evolution, it will be in its ground state, the usual harmonic oscillator ground state that you observe. But as you evolve it with time, you see that these scaling parameters B basically cause the wave function to deviate from its initial ground state. And this will turn out to be excited in the instantaneous eigenbasis of the same particular mode later on. And you also notice that now when you write down the full wave function of the system in terms of the original physical coordinates, you see that it's entangled, in the sense the wave function is no longer separable. And you do not have an individual description, independent description of any one of these oscillators which is independent of each other. Now, about the scaling parameters that I introduced here, these scaling parameters are basically solutions to the Markov-Pinay equation, which are highly nonlinear. And you see that the solutions basically take up 3 different forms depending on the stability regimes that you look at. For instance, you focus on the sign of the omega square as it relaxes to a constant value, for instance. And then the sign of that final value of omega square will basically determine what kind of functional form the scaling parameters take. For instance, omega square greater than 0 leads to the stable oscillatory behavior of the scaling parameters. And omega square going to 0 will lead to a linear growth, and omega square being negative will lead to an exponential growth in the scaling parameters. Now, why are these stability regimes relevant? Because as you will see, during inflation, as I mentioned earlier, the modes that exit the Hubble radius at some point, the modes that remain within the Hubble radius during the expansion are basically stable and oscillatory, and the modes that cross the radius get inverted. So keeping this in mind, so what I would like to address is the loss of quantum features that are present in these fluctuations, and the primary method or the primary medium of this analysis is decoherence. So what I mean by that is basically you can look at the density matrix of the system and view it as an ensemble of states. You have, in one case, a quantum ensemble where you have off-diagonal terms in the density matrix, and decoherence basically refers to a scenario where all these off-diagonal terms drop out, and finally you have a density matrix that resembles a classical statistical ensemble. And a good way to measure the degree of quantum decoherence you have in your system is by looking at the purity of the density matrix. And if you look at the purity, if you see that it's 1, it's pure, and if it goes to 0, it essentially means that it's decoherent. Now, what is interesting is that, as I mentioned earlier, the wave function that you looked at earlier is entangled in the physical coordinates. So now if you divide this total system, the scalar field, into two spatial regions, A and B, what you get is basically a full density matrix, and from there, if you remove degrees of freedom corresponding to either A or B, you get a reduced density matrix. And basically, entanglement entropy, which is a measure of entanglement between the systems A and B, also turn out to be a good measure of the decoherence corresponding to the reduced density matrix. So in a way, what entanglement entropy actually measures is the decoherence of system A because of B, or vice versa. It's symmetric across the bipartition. Now, another way you can measure instabilities is by looking at Loschmidt echo, which is basically a quantum analog of looking at the distance between two classical phase space trajectories, especially in a chaotic system. So in chaotic systems, this distance turns out to be exponentially increasing with a growth factor that can be related to Lyapunov exponents. In our case, in the quantum case, what we look at is basically the distance in the Hilbert space captured by this scalar, by this dot product. And basically what happens is you look at two slightly different Hamiltonian evolutions, and you compare the states, and if that corresponds to an exponential decay, that can be associated with a quantum Lyapunov exponent arising from an instability in the system. And as it turns out, in our case, this exponential decay of the Loschmidt echo actually happens when you have an inverted mode in the mix. And the decay rate can be exactly related to the magnitude of the inverted mode. So basically what you have here, when you finally look at the behavior of entanglement entropy for an arbitrary subsystem size n, you have a linear growth corresponding to inverted modes in the system, you have a logarithmic growth corresponding to a 0 mode in the system, and you have a stable oscillator behavior corresponding to stable modes, which eventually gets suppressed in the presence of other instabilities. So now when you sum up what you can observe from entanglement entropy, you see that for a certain subsystem, once your subsystem size is large enough, what happens is this entanglement entropy actually mimics its classical counterpart, which is known as the Kolmogorov-Sinai entropy. So a little bit about Kolmogorov-Sinai entropy. What it basically looks at is the growth of statistical entropy in a classically chaotic system. And as it turns out, for such an entropy, the growth rate of the linear growth of entanglement or of statistical entropy is basically the sum of all the positive Lyapunov exponents in the system. And in this case, what we see is that entanglement entropy mimics the exact same behavior when there are inverted modes in the system, and secondly, when the subsystem size is large enough. And another thing that we notice is that if we look at entanglement entropy for a small subsystem within the full system, we see that in this exact same limit where the subsystem size is large enough and there are inverted modes in the system, you see that it converges with full system measures such as circuit complexity and ground state fidelity of the full wave function of the system. Now, other things that we notice, for instance, include, for instance, something to do with the scaling behavior of entanglement entropy. So in quantum systems in general, in the ground state, entanglement entropy is supposed to follow an area law. But what we observe here is that if there's some kind of time dependence in the system, and finally you have, in this case we are looking at stable modes, if you have an initial, if you have a final relaxing stable mode, if all the normal mode spectrum corresponds to stable behavior at the end of your evolution, you see that the entanglement entropy basically has a linear growth followed by linear descent. And during this linear growth, you see that the entanglement entropy changes from an area law for 1+1 systems in this case to a volume law in 1+1 dimensional systems, and it has a periodic behavior back and forth. And what we also see in the inverted mode case, also in the zero mode case, is that there is a progressive deviation from area law, but in order for it to settle to a volume law at the end, you have to probably evaluate it to from all the way to t tends to infinity, which in this case is very difficult because your the scaling parameter solutions are exponentially growing with time. So, so what this basically means is that if there are inverted modes in your system, you see that entanglement entropy classicalizes, and the entanglement entropy also mimics thermodynamic entropy, wherein it has an extensive scaling of with system size. Now, the question is whether this will be enough to identify quantum to classical transition, and the answer is no. Apparently, one more signature that we can look at is squeezing. So I don't know if I have much time, but okay. So in that case, I'll just roughly go through what it means. So if quantum systems have a phase-space representation in the form of Wigner function, as opposed to fixed classical phase-space trajectories. And a good way to measure whether a system approaches classical behavior is by looking at the level of squeezing. So what happens is when the modes cross event horizon, when the modes cross the Hubble radius, we also see signatures of squeezing, wherein the Wigner function squeezes and the peaks of the Wigner function aligns with the classical phase-space trajectories. And we have devised a way in order to look at or measure the squeezing for a multimode Gaussian state. And we see that the classicality criteria, which is something that Morikawa and later Podarski and Starobinsky proposed, was that you can identify a quantum to classical transition asymptotically by looking at decoherence, which here can be captured by entanglement entropy going to infinity, and squeezing, which here is captured by a parameter which we call log classicality, which I won't go into at the moment, which also goes to infinity asymptotically. So here's an example. In 3+1 dimensions, if you consider a scale factor A of t, you can, as I mentioned earlier, bring it to a harmonic oscillator lattice form. And then when you look at evolutions such as a Tanich evolution, where you have asymptotically constant A of t in the past and the future, you see that there is no decoherence, there is no runaway decoherence, there is no runaway squeezing. But on the other hand, if you look at de Sitter expansion, you see that there is a runaway decoherence and a runaway squeezing. So in order to sum up, the criteria that we look at here is once you have a vacuum state and you run the evolution with time, a good way to measure or good way to identify quantum to classical transition is by looking at decoherence and squeezing. And what we showed is that basically inverted modes, which correspond to modes that actually get stretched out beyond the Hubble radius, inverted modes basically cause entanglement entropy to classicalize for sufficiently large subsystem size. And we also see that there's a progressive deviation from area law to volume law as this inversion happens. And in 3+1 dimensions, we were able to show that the de Sitter expansion satisfies this criteria for quantum to classical transition of fluctuation. So what we have built here is a framework, and what you can do in order to extend this is by accounting for non-Gaussianities, for instance, in a later work. Or maybe you can look at the same kind of dynamics in causal sets approach as well. And finally, what we will also be looking at includes area law to volume law transition in 3+1 dimensions, generalization to higher spins, and finally, we also want to apply this to black holes and see what happens. Yeah, thank you.
Any questions? Yeah. Here.
Thanks for the nice talk. I just have a quick question. You mentioned in the first part that these Lyapunov exponents tell us about chaotic systems. But in this case that you're looking at, it's just an instability, right?
Yeah,
so it's not a chaotic system.
Yeah, it's not a chaotic. It's fully integrable. It's not chaotic, but you can, in principle, still calculate Lyapunov exponents for instabilities. In that sense, it's called a quantum Lyapunov exponent, but it's not chaotic.
Right. So how do I differentiate between the two? If I did not know that this was an instability, is there a way to differentiate between chaotic systems and?
I suppose there are, but I don't know at the moment. But it's more of a condensed matter problem. I wouldn't know, but I'm sure there is.
Okay. Thank you.
A way to differentiate. Yeah. Thank you.
Okay. Then let's thank our speaker again.
Thank you.